This video is about enthalpy and its amazing property as a state function. So state functions turn out to have really useful properties, and we're going to exploit those so that we can understand how to calculate enthalpy changes for a reaction. So first, let's talk a little bit about what state functions are. So as a technical definition, state functions depend only on the state of the system, sort of where it is at any particular moment in time, and not on its history, where it's been, or its path, how it got to where it is. So some examples of things that are state functions are temperature, pressure, volume, internal energy, and enthalpy, among others. So each of these properties only depends on the state of the system at any moment in time. So for example, if a glass of water has a temperature of 68 degrees Fahrenheit, it doesn't matter how that glass of water got that temperature. That temperature is not going to be affected by whether it was cooled down to that temperature or heated up to that temperature. It doesn't matter what its past history was. So let's look at an example to help make this a little bit more clear. So imagine that we've got two hikers trying to climb up to the top of this mountain. So they're both starting at 3,000 feet, and they're going to climb up to the summit at 10,000 feet. So the hiker on the left is going to use this red path. So this red path has a fairly low grade, lots of switchbacks, and it's very long. It's 12 miles. The hiker on the right is going to use this really steep path. So this hiker is going to have to climb on his hands and knees up some rocks. It's really steep, but it's only 5 miles. So if we think about the total change in altitude that both these hikers is going to experience as they climb from the bottom of the mountain to the top of the mountain, well, that's written over here. So here I've got altitude written out on this axis. So this is my altitude axis. And over here I'm looking at delta, which means change. So remember, delta in science is always representing a change. So this is the change, and what do I have in parentheses? Altitude. And so what is that change going to be equal to? Well, it's equal to the final altitude, and up here at the summit, when we finally get our hiker up there, woohoo! Plant the flag. All right, plant the flag. Yay. Okay, when he finally gets up to the top, that's going to be the final altitude at 10,000 feet. What was the initial altitude? 3,000 feet. And so we take the difference in those to figure out the total change in altitude. So 10,000 minus 3,000 would be a 7,000 foot climb. So this hiker is going to be covering quite a lot of vertical distance. But notice that the number of miles that they actually walk will be very different. So they will have the same altitude change, but different paths. So the path depends on actually how you walk, and in this example, altitude is like a state function. So altitude just depends on where you are vertically above the surface of the earth, not how you got there. So if this first hiker had stopped only halfway up, then he would have had a certain altitude, and we could calculate his altitude change, delta A. Now there's another interesting property of state functions that can be demonstrated in this example. So let's imagine that we can break the altitude changes of this red path up into little small bits. So we're going to call this delta A1. So A stands for altitude and delta for change, and 1 because it's the first one. So we're going to look at the altitude change from where the hiker starts to this first switchback, and then from this first switchback to the second switchback. That's delta A2. And then we would have delta A3, and so on, all the way up to the top of the mountain. So what is the total altitude change? Delta A, we'll let A be altitude. Well, it's just going to be the sum of all the little altitude changes for each switchback. Delta A1 plus delta A2 plus delta A3, and so on. So I'll say plus dot dot dot. Okay, so any of these state functions up here, any of their changes could be broken down into a smaller set of steps, and we could just add the changes for each of those steps to get us the total. So that's a very important property of state functions. Because it doesn't matter whether you get to the top through the red path or the blue path, we can think of breaking this process down into as many steps as we want. And so that's exactly the kind of thing that we're going to do when we think about chemical reactions. So what I'm going to draw here is a little blob, and this represents So let's say our reactants, and we're in state, let's say A. So some particular set of conditions. And what's going to happen is those reactants are going to be converted into products. So I'll draw a different kind of blob over here, P for products, and that's what we're going to call state B. All right, so maybe a different set of conditions because we have different pressures, perhaps different temperature now, whatever. Anyway, so we've converted our reactants into products. So we want to know, well, what is the enthalpy change for this process, this delta H? And sometimes we put a little subscript R right here to remind us that this is for a reaction. We might want to know what this is. So, oh, that's supposed to be a question mark. It's not 3. Question mark. So remember that enthalpy is related to the amount of heat that goes into or out of a reaction when that reaction is conducted at constant pressure. So I talked about these states A and B being different, but in one way they're going to be the same. They're going to be at constant pressure. In that case, delta H is equal to the heat that goes into or out of the system. So we might want to figure that out, predict that. Well, maybe we can think of these reactants being converted into something else first. So I'm going to call this state 1. So we go from state A to state 1. So these reactants get converted into something else. So there's a delta H for that process, and we'll call that delta H1. And then we go from state 1 maybe to the products. So we're able to convert all the way from whatever this state is into the products. And there's a delta H for that process that we'll call delta H sub 2. So because H is a state function, just like we saw with altitude, what we've gone from this initial state to this final state. So just like we went from the bottom of the mountain to the top of the mountain through this particular pathway. And here's another pathway that leads from the same state A to the final state B. And so what is the delta H for that step? Well, it has to be the sum of the delta H's for each step along the way. So the delta H for this two-step process has got to be equal to the delta H for this one-step process. We can draw another picture to kind of represent that. So this is called an enthalpy diagram. So enthalpy is on the y-axis here, and then we put little lines to represent the enthalpies of different states. So let's say that my reactants start here. Let's say that my products are here. So the delta H would be the difference between these two states. And in this case, as I've drawn it, delta H is going to be negative, so less than 0, because the enthalpy of the products is lower than the enthalpy of the reactants. We would say that in terms of energy, the products are more stable than the reactants, lower in energy. All right, so now imagine that there's a different process. So we're going to convert our reactants into something else. All right, so imagine that there's some other reaction that takes place that converts our reactants into something else. And imagine that that step, we'll call that delta H1, is endothermic, greater than 0. And then imagine that I can go from state 1 all the way to the product state here. Then in this case, that would be delta H2, and that would be an exothermic step, less than 0. So we would release heat on that second step. So you can see sort of graphically here that the difference between these two line segments that I just circled, right, is the total enthalpy of reaction. So if we just add up these two delta H's, we will get this delta H. Now we have to be careful with our signs, right? This one is going to be positive because we're going up, and this one is going to be negative. When we take a positive and add it to a big negative number, we'll still get a negative number. So that will give us our negative delta H that we expect for this exothermic reaction. So that's the beauty of state functions and how they can be really helpful in helping us think about enthalpy changes. So let's make this concrete by looking at an actual example. So imagine that we've got this reaction. Okay, so in this reaction we've got hydrogen gas and chlorine gas reacting to make 2 moles of hydrogen chloride gas. And we're interested in thinking about, well, what is the delta H for this reaction? We might like to calculate the delta H for that reaction. So is it endothermic? Is it exothermic? What? Well, what we're going to do is make use of Hess's law. We're going to imagine breaking this reaction down into 2 steps. So the first step, what we're going to do is we're going to take these reactants and we're going to first convert them into their atoms. So we're going to get 2 moles of hydrogen atoms in the gas phase plus 2 moles of chlorine atoms in the gas phase. All right, so that's step 1. And because we're breaking bonds in going from H2 and Cl2 to 2 H atoms and 2 chlorine atoms, this step, anytime you break bonds, is going to be endothermic. So delta H will be positive. We've got to put energy into the system to pull these atoms apart. Now what we're going to do in step 2 is we're going to imagine that these atoms can come back together in a different arrangement. So we're going to take our 2 hydrogen gas atoms and our 2 chlorine gas atoms, and we're going to let them come together to make these 2 HCl molecules in the gas phase. So that's going to be step 2. And in step 2, because what we're doing, the only thing that we're doing is making bonds between hydrogen and chlorine, we know that anytime you make a bond, you always release energy. So this will be exothermic. And then we can figure out, if we could figure out what the delta H's for each of these steps were, then we could calculate what the delta H for this overall reaction is just by adding them together, because that is the property of state functions. So we just add up the delta H's. That should be equal to the overall delta H. By the way, I forgot to mention this property of adding up all the delta H's for each step to get the total delta H. Even though that's a property of H as a state function, it gets a special name. So it's named after this guy Hess, and so this is sometimes called Hess's law. Hess says that the sum of the delta H's of each step in a process equal the delta H for the overall process. Okay, so let's think a little bit about this reaction. So we've got an endothermic step and an exothermic step. So let's see if we could calculate this. Well, this reaction, Cl2 going to 2Cl gas, well, that's a reaction that can actually be done. It can be measured, and it's related to the bond energy of Cl2. So this reaction is the bond energy of Cl2 because we have to put in that much energy to break the bond between these chlorine atoms, 2 chlorine atoms that are bonded together. So if you have 1 mole of chlorine gas to make 2 moles of Cl2, the delta H for that process is going to be a positive 243.4 kilojoules per mole. And I'm going to put another subscript on this mole. I'm going to put RXN, that stands for reaction, and so that means per mole of reaction as balanced. So this is how much energy gets absorbed because it's positive, so that's energy going in. This is how much energy gets absorbed when you take exactly 1 mole of chlorine gas and you break it down into exactly 2 moles of chlorine gas atoms. Okay? So if you happen to have 4 moles of chlorine gas, you're going to have 4 times as much energy input in order to get that reaction to happen. Okay, similarly we can look at the bond energy for H2. So the H2 bond energy is a positive 435.3 kilojoules per mole of reaction. All right, so just comparing these two numbers out of interest, this tells us that the bond between hydrogen atoms is stronger than the bond between chlorine atoms. We might have guessed that because they both involve the sharing of a single pair of electrons, but the hydrogen atoms are much smaller, and so the bond between those 2 hydrogen atoms is going to be shorter, and we've learned before that shorter bonds are typically stronger bonds. Okay, so if we add these two numbers together, we should get the enthalpy change for what I was calling step 1, right? Because step 1 involves hydrogen breaking up into 2 hydrogen atoms and chlorine breaking up into 2 chlorine atoms. So if we do both of these 2 steps together, we should get the overall step 1. So we could add those 2 things together. So this is how much energy you would have to put in to break all the bonds in those molecules. So let's just figure out what that total is. So we're going to add these up, and the delta H for step 1, which is this step right here, remember step 1, is going to be the sum of these numbers, which is 678.7 kilojoules per mole of reaction. Now let's think about putting these atoms together. So taking H atoms in the gas phase and combining them with chlorine atoms in the gas phase to produce a mole of HCl gas molecules, well, that process is just the reverse of breaking this bond. So again, we can measure the bond energy of HCl, and the reverse of that is how much energy we're going to get out when that bond is made. And so this delta H is negative 431.6 kilojoules per mole of reaction. So notice that this bond in HCl is stronger than the bond in chlorine, but a little bit weaker than the bond in H2. That again might make sense because we've got a bond that's of intermediate bond length. All right, so the negative sign here, just as a reminder, is telling us that this is an exothermic reaction. So the signs always tell us about direction, and negative means out, going away. Positive means in, coming in. So this would be energy released from the system when this bond is made. Now you might think that this is the step 2 reaction that we were looking at up here, but it's not quite, because we had 2 moles of hydrogen atoms reacting with 2 moles of chlorine atoms to give us 2 moles of HCl. Why does it have to be 2? Don't we usually divide this out to get the smallest whole number set for balanced reaction? Well, we can. This is still a balanced reaction, but the reason that we need it this way is because we are trying to make, according to our initial balanced reaction that we want to know the delta H of, we are trying to make 2 moles of HCl. So because of that, we want to form 2 moles of HCl. So this reaction right here is only for 1 mole of HCl. So how would I make it appropriate for 2 moles of HCl? Well, I just have to go through and multiply all these coefficients by 2. But if I'm making twice as many bonds, it stands to reason that I'm going to make twice as many. I'm going to release twice as much energy, right? If I make twice as many bonds. So the delta H for now step 2 is going to be equal to negative 863.2 kilojoules per mole of reaction. That's what we get when we take negative 431 and multiply it by 2. So putting these two things together, we can now calculate the delta H for our overall reaction, which is hydrogen gas and chlorine gas making HCl gas. So the delta H of the overall reaction is delta H1 plus delta H2, and I've just calculated what those are. So delta H1 is a positive 678.7 kilojoules per mole of reaction. And then I'm going to add that to delta H2, which is a negative. So be careful here. I've got a plus and a negative. In thermochemistry, you really have to be careful with your signs. So always carry your signs and be careful when you type these things into your calculators. Okay, so when I take 678.7 plus a negative, that's the same as subtracting. So this number is larger in magnitude and negative, so that's going to give me a negative number overall. So if you type this into your calculator, 678.7 plus a negative 863.2, you'll get negative 184.5 kilojoules per mole of reaction. So let's look at that on an enthalpy diagram, just to think about what all is going on here. So this line right here, this is going to be H2 and Cl2. So they have this much enthalpy. So I just drew that in an arbitrary place on this line. Now what we're going to do as our first step, we are going to put in some energy so that we end up with 2 H atoms plus 2 Cl atoms. And we had to put in a positive 678.7 kilojoules of energy. Okay, so we are 678 kilojoules of energy higher. Now what we're going to do is release some energy. So we're going to go all the way down here. And now we've gone downhill in enthalpy by 863.2 kilojoules per mole of reaction. And that's when we're going to have our 2 moles of HCl. All right, so these are the two steps, step 1 and step 2. So we first break the bonds between the atoms to form just the atoms. Then we put the atoms together in a different way. And the difference between these two lines then is the delta H for this overall reaction. And you can see how it's the sum of these two numbers, because this distance plus this distance is equal to this distance, right? So we can see that sort of graphically. So that brings up an interesting question now. Does this reaction really happen this way? Do the molecules first break apart into their atoms, and then the atoms come back together in a new way? Well, no, probably not. But the beauty of state functions is that it doesn't matter. We can calculate it as though it does. So using these bond energies, which are something that we can measure, we could calculate or predict an overall delta H of reaction. And that's a pretty powerful thing to do, because without actually having to measure that reaction, we can make predictions about how much heat is absorbed or released when that reaction happens. And that might be something you want to know before you go out and try a reaction in your backyard, because if it's going to generate a lot of heat, you might want to worry about that, right? Because you don't want to set anything on fire. Okay, so that's using delta H as a state function. I have one quick other topic to talk about, and that's standard state. So I told you how enthalpy depends on conditions, and so if we measure the same reaction under different conditions of temperature or pressure or something like that, we're going to get different answers. So what chemists have done is we've agreed on a standard state so that we're going to measure things all relative to that standard state before we put them into tables. And then if we need to, we can calculate them for different states. But we're going to tabulate everything in an agreed upon standard state. So states depend on things like temperature, pressure, and amounts of substance. So when we tabulate reaction enthalpies, we're all going to tabulate them under standard state conditions. So the first thing that we're going to specify is temperature. Most thermodynamic tables specify temperature at 25 degrees Celsius, which is a typical room temperature, and that's 298 Kelvin. So if you don't know, you should assume that that is the value. Otherwise, folks will write typically next to the delta H the temperature at which that delta H was measured, so maybe like 1273 Kelvin if it was at some much higher temperature. So we'll put as a little subscript what the actual temperature is. So we should assume that our standard temperature is measured at 25. Then we also agree upon standard state amounts of reactants. So we're doing this for certain amounts of reactant. And in this case, we want all partial pressures to be equal to 1 bar of pressure. So 1 bar of pressure is really close to 1 atmosphere of pressure. So 1 bar is equal to 0.9869 atmospheres. So for practical purposes, it's the same as an atmosphere, but in careful work, we'll want to distinguish between these. So partial pressure, so the bar is a unit of pressure, and we want each gas to be present at 1 bar pressure. So that's how much in terms of amount we want. So what does a partial pressure mean? Well, that means that we've got a container of a certain size, a certain volume. We're going to put gases in here. So let's imagine this blue gas in here. We're going to put it up there until that blue gas has a pressure of 1 atmosphere. Now if we were to go in and add a different gas to this box, so let's say these little yellow molecules, well, now the pressure is going to be higher, right, because we've added this other gas in. But the partial pressure of the yellow gas, we can imagine that's the pressure that it would exert if it were in this box by itself. So let's go in and pick out these blue molecules, take them away, and now we're going to measure the pressure inside that box for the yellow molecules, and that's the partial pressure of those yellow molecules. And then the total pressure would be the partial pressure of the yellow molecules plus the partial pressure for the blue molecules. Okay, so we add up the partial pressures of each gas, we would get the total pressure inside there. And what we want in terms of standard state is to have all pressures at 1 bar. For solutions, so if you have things that are not gases, so we need to specify something about amount. All solutions will be 1 molar in concentration. So remember, molarity, M, is moles per liter. So that means we have 1 mole of each substance divided in, dissolved in 1 liter of solution. And so those are the standard state conditions. And so whenever we talk about a standard state enthalpy, to remind people that we are in standard state, we're going to put a little superscript 0 up here. So that superscript 0 means standard state amounts. So partial pressures of 1 bar and molar concentrations of 1 molar. So that means standard STD state. So our standard state. So most often when you look up values in a table, you're going to be looking up standard state enthalpies. So for example, these numbers that I gave you before for these bond energies, those were actually standard state enthalpies that I found. So that's how we can think about standard states and how we can use Hess's law and this important property of state functions to calculate enthalpy changes for reaction, even if it's not the way the reaction actually occurs. So reactions don't actually first break up into atoms and then reassemble into the product molecules. But we can assume that they do and calculate the energy based on this state function property.